Okay, so I'm going to ask this question. How do we know how smart AI systems are? And is that even the right way to think about what they are? So, how do people evaluate cognitive capacities in LLMs? It's the simplest method, and in fact, perhaps the one that you've used is just to look at their behavior, chat with them. Do they seem like they're intelligent? Do they seem like they understand you? And this is sort of like a mini Turing test. But of course, we all know that humans are very prone to project intelligence, understanding, even consciousness onto entities that communicate with us in natural language. Um, this is called the Eliza effect, named after the original chatbot Eliza, which was developed in the 1960s and pretended to be a psychotherapist. Very dumb chatbot. It didn't have any intelligence whatsoever, but people would chat with it and it would respond with understanding like questions, and a lot of people thought that it really understood them. So this kind of subjective approach doesn't always give you insight into actual cognitive capacities. So instead of doing this subjective test, many people have devised various benchmarks for different cognitive abilities. And in fact, now we have this issue that AI systems are surpassing humans on most of these benchmarks. This was reported last year in Nature, and they showed this interesting plot, which shows over the years um, on different kinds of benchmarks, and you can see things like image classification, visual common sense, reading comprehension, multitask language understanding, etc., that by the 2020s, these systems, now powered by transformer networks and large language models, have in many cases surpassed or matched humans on these various benchmarks. But this can be deceiving. When people name the benchmarks, they name them after the general capacity that they hope their benchmark is measuring, like reading comprehension or visual reasoning. But it turns out that just because a machine does well on a benchmark called visual reasoning doesn't mean that it has a general capacity for visual reasoning. There might be other reasons why it does well on a particular benchmark. And in many cases, people have showed that there is data contamination, which means that the benchmark itself, questions from the benchmark or very similar kinds of items are present in the training data, and that it gets harder to figure that out when you don't know what the training data is, which is the case for all the most capable models. There's also many times what people call shortcuts, that is, ways to answer the questions without having a general capacity for a general ability for this capacity, or approximate retrieval is another word that people use for being able to spot similarities between the training data and the items. So people in AI often will say benchmarking in AI is broken. That is, showing that these machines are surpassing us on various benchmarks really is not a good predictor of their general abilities in the real world. A new approach now with so-called reasoning models is to have them explain their thinking. Maybe you've played with some of the new reasoning models like OpenAI's O1 or O3, or Gemini's what they call extended thinking. These terms are actually used very promiscuously to describe what these systems are doing. OpenAI describes it as reasoning models think before they answer, producing a long internal chain of thought before responding to the user. And in their systems, the system will show you some of its chain of thought. And OpenAI also proclaimed that users told us that understanding how the model reasons from reading its internal thoughts, if you will, uh, not only supports more informed decision making, but also helps build trust in its answers. But the only problem is that these reasoning models, it turns out, when you actually look at them in more depth, what they generate as their reasons and reasoning traces may or may not be related to what they're actually doing. And this is a recent paper from Anthropic showing that the traces that they generate are actually sometimes not well correlated with what these systems are actually doing under the hood. And that their chain of thought reasoning is not faithful to their actual operation. So I would say, explaining their thinking, they can't actually do this. So don't trust what these reasoning models have to say. Well, okay, so another possibility is that we actually have to look under the hood and try and figure out exactly how they're doing what they do. So there's been a sort of sub-industry of AI, current AI, called mechanistic interpretability, which is trying to figure out when an AI system does some task, what exactly in terms of the neural network weights and activations are giving rise to that ability. So Ilya Sutskever, one of the co-founders of OpenAI, he wrote this, or he actually said this in an interview: when we train these neural networks to predict the next word in lots of different texts, what they are learning is what he calls a world model. It's a projection of the world. The text is a projection of the world. It's learning, and he gets kind of poetic here, it's learning more and more aspects of the world, of people, of the human condition, their hopes, dreams, and motivations. It learns a compressed, abstract, usable representation of that. Okay, so his idea is that just by this training objective of predict the next token in sequences over a huge corpus of human-generated text, that the model is abstracting a model not of just language, but of the world itself and how the world works. That's akin to the kinds of internal models humans might use to understand and predict what's going to happen in different situations. But what's the evidence for this? This is a really ambitious claim, but what's the evidence for this? Well, one major influential set of papers on emergent world models in LLMs came from studying a particular kind of board game called Othello. I don't know if many of you are familiar with Othello. It looks a little bit like this. This is it's played on a board, an 8x8 board. It starts out this configuration on the left with black tiles and white tiles in this center array. And then at each turn, the black tile player moves, and then the white tile player moves. They take turns. And at each turn, the player has to move so that their pieces surround a piece of the opposite color. So you can see in B, black has moved to square E3, and since it surrounded the white tile on E4, that tile flips its color. Okay, and then in C, white has moved to D3, and the black tile at D4 flips its color because it's surrounded. So that's how Othello's played, and you keep playing until no more moves can be made, and then the player with the most tiles of their color wins. So this was an experiment in this very constrained world of Othello to try and see if a transformer network like those underlying language models could learn a world model where the world is the Othello game just from sequences of tokens. So what these authors did was they generated many sequences of tokens that represented an Othello game, all the moves in an Othello game. And you can see there, E3 is moving a black piece. You always start with black to the position E3, and then white moves to D3, then black moves to C5, and so on. And these 20 million simulated games were generated by a game generator, and were fed as token sequences of different lengths to this transformer network. And the transformer's task was just like ChatGPT or anything else, predict the next token in the sequence. Okay, so the transformer doesn't know that these tokens represent game moves. It doesn't know there's a game or a board or players or colors or anything. It's just getting these sequences of tokens. So this is meant to be a sort of microcosm of these larger language models that input tokens of language and presumably learn some kind of model of the world. And after this network is trained, after the transformer network is trained, then the question is, what has it learned? And it's able to do a good job of predicting the next token after those 20 million training examples. And so what the authors do is something equivalent to what a neuroscientist might do: stick a probe in your brain and see how to model the stream of activations that come out. And so what they do is they train a linear classifier to input the activations after a given sequence is input. So let's say those 3 moves are input. Now the question is, what does the board look like? Well, the transformer didn't know there was a board. It was just trained on token sequences. But what these authors were able to show was that what the system seemed to have learned was the configuration of the board. It was able to decode from this linear classifier was able to decode from the activations of the trained neural network the current contents of each board square. So this was at each layer what the accuracy was of predicting the configuration of the board from activations of this 8-layer transformer model. Okay, and I also would say that the authors show that they can do what they called causal interventions. They can change the activations in the transformer and see the board configuration prediction from the probe change accordingly. So people in AI were very excited about this result. Chris Olah, who's one of the founders of Anthropic, tweeted that this Othello paper was clear evidence of a language model developing an internal world model. Andrew Ng, who's a pioneer of deep learning, said, do large language models really understand the world or just give the appearance of understanding? It's a big question. And he says that this evidence from the Othello experiments show that LLMs build models of how the world works, which makes me more comfortable in saying they do understand. So maybe this is the answer to figuring out how machines do what they do if we could only just probe them and figure out their internal world models. But a problem is that when a group of people looked further at what exactly this model had learned, they discovered that it hadn't really learned a compressed model of the board the way that you might have in your mind, but rather it learned what they called a bag of heuristics, which are specific rules. So the neurons in the transformer network had learned, if we can describe them in language, they learned very specific rules, like if the move A4 was just played and B4 is occupied and C4 is occupied, then predict, that certain squares are black or white. And it had a very large collection of these rules that collectively were very good at predicting the contents of the board. So these internal so-called world models seem to not be the kinds that we humans would form, but rather very uncompressed, very large sets of statistical associations like this. And it turns out that other people have found similar results, for instance, in trying to understand how these systems can perform certain kinds of arithmetic, that they don't create sort of a internal calculator that uses the kinds of algorithms that our calculators might use to do arithmetic, but rather they have these kinds of very specific heuristics that are not very generalizable and can make errors. So it's not clear how robust and generalizable these models or heuristics are. So another approach that people have used to evaluate cognitive capacities are to adapt experimental methods from cognitive science. So Mike Frank, who's a developmental psychologist at Stanford, wrote a very nice piece called Baby Steps in Evaluating the Capacities of Large Language Models, in which he said that, well, we have these, developmental psychologists who have been asking questions about what he called another kind of alien intelligence, that is human children. Children that, can't really tell us exactly how they're thinking. And he proposed that methods from this research can help us probe the capacities of LLMs. And Anna Ivanova, a psychologist from Georgia Tech, wrote a paper called Towards Best Research Practices in AI Psychology, where she gave a list of do's and don'ts for experimental methodology. So some of these are very common sense ideas, like use careful controls. Don't just report the accuracy of your AI system on some benchmark, but try doing some control experiment. Well, that makes sense, like in science, but people in AI don't tend to use very good scientific methods when they do these evaluations. Or compare model and human performance, or check whether a model generalizes beyond a single test. Okay, very common sense. So here's a case study of that I and one of my collaborators did. So there were some claims that GPT models had developed emergent capabilities for analogical reasoning just by being trained on this next token prediction. And this was a paper from a group at UCLA that was published in 2023. And what they showed is on several domains in which they tested either both people and GPT models for analogy making. Here was some what are called simple letter string analogies, what they call digit matrix problems, and story analogies. I don't have time to give you the details, but if you're interested, I can tell you more later. GPT-3, which is the one they were studying at the time, and they also extended this to GPT-4, either surpassed humans or got close to humans on these different domains of that psychologists have used to study analogy making. And their claim was, our results indicate that GPT-3, unlike any other neural network previously tested, displays a capacity for zero-shot analogical reasoning across a broad range of tasks. So the question is, though, is it actually doing analogical reasoning in a robust and general way? So here's an example of one of the domains they looked at, which are these letter string analogy problems, which are purported to capture something of more general human analogy and abstraction abilities. So here you take one string and transform it into another string, and then you ask the solver to make an analogous transformation to a third string. So here most people would say IJKM. So transform the rightmost letter into its successor in the alphabet. Or here, a IJKL, change the double letter into a single letter. Or here, IJKL, fix the sequence. And this domain is pretty open-ended in terms of the kinds of patterns you can look at. So my colleague and I, Martha Lewis, my collaborator, did a study trying to take into account the kinds of principles that Mike Frank and Anna Ivanova had proposed for experimental methodology to evaluate the robustness of this kind of reasoning. So we tried a couple of controls. So one of the controls was to change the problem a little bit by having a counterfactual world in which the alphabet was slightly different. So by shuffling two letters, the M and the E, and we said, take this new alphabet, and we're going to give you the analogy task in this new world with this new alphabet. Now solve it. And we translated the old analogy tasks into these new analogy tasks. And presumably, if you're able to do general abstraction in order to solve analogies, you should be able to do well on these kinds of problems. Another set of problems is where we had a counterfactual world where alphabets consisted of symbols rather than letters. Okay, and we tested humans and the GPT models on these different domains. And we found that while humans, these are these blue dots, I hope they show up here, stay relatively constant in their abilities to solve these problems, the various GPT models go down quite a bit, and especially with this symbol alphabet. We also experimented with similar variations on other analogy domains and found similar results. And other people have done the same kind of robustness tests with control experiments that show a similar lack of robustness for AI performance on various benchmarks. So the take-home message is that these LLMs seem to be better, often dramatically, on solving reasoning tasks that are similar to those seen in the training data or that allow certain kinds of shortcuts. This is not necessarily different from humans. Humans also are better at solving reasoning problems that are framed in terms of familiar ideas, but humans do seem to be better at adapting their understanding to new domains. So in LLMs, this reflects a failure of conceptual abstraction and reasoning. So the question is, how can we best sort of inspire better, more robust reasoning, and how can we test it in these systems? So I just wanted to, for the last part of my talk, to talk about a domain that has been proposed for this, called the abstraction and reasoning corpus, which maybe some of you have seen, which was proposed by Francois Chollet from Google. It's a domain for open-ended concept induction and abstract reasoning. It has a little bit of an interesting sort of trajectory in the AI world. So this domain is uses these two-dimensional grids with colored squares. It's sort of similar to the letter strings, except now we have these sort of images where one grid, I give you here 3 demonstrations of a transformation. One grid transforms into another grid, and I show you 3 transformations, and there's some underlying rule. And I think most of you can see here what the rule is. It requires figuring out that there is some kind of object, where the object that maps onto the same object in different demonstrations, and that there's some kind of extension from one end of the object to a boundary using a color that's the same as the color at the sort of bottom of the object. Okay, so most people will find that very easy. Another problem puzzle is this one. I'm hoping you can you all see what these okay? Okay, so usually in talks I let people solve these and propose solutions, but I only have 5 more minutes. So this is a shape invariance problem where shapes of different kinds of shapes are colored different colors, even if the shape is different size or orientation. And in general, Chollet created 1,000 tasks like this, of exploring different kinds of spatial and semantic concepts. He published 800, and 200 were held as a hidden test set, and he offered a prize for $600,000 prize for a program that exceeds 85% accuracy on one of the hidden or private test sets. Okay, so that's a good amount of money, and a lot of people competed for this had programs in different ways, and 85% came from studies of humans and how well humans did. And in this competition, the best team got about 55% accuracy. They actually, in order to get the money, they didn't get the grand prize, but they were going to get first place in this competition. They actually decided not to submit their program and open source it, which was a requirement, because they were going to start up a company to, to actually try and solve these problems. And you might think, well, it's weird to have a company that's just going to try and work on this kind of little puzzle set. But you might remember that DeepMind, before it was acquired by Google, what they did was they worked on Atari video games and were able to do well on these very simple kinds of video games that were playing things like Pong or Breakout. And then Google, because of that result, acquired them for $500 million. So a lot of people were thinking that the similar kind of thing might happen with this ARC set. But right after this came out, OpenAI released their O3 reasoning model, which was run on a different private evaluation set. And the best version of this model attained 88% accuracy. However, it attained it at a very big cost. It cost about $3,000 per task. You know, I just gave you 2 tasks to solve. It cost $3,000 in compute per task. And for each task, it had to generate, over the whole data set, I think, it had to generate 5.7 billion tokens, which is a lot. Okay, so that was very surprising that this worked so well. But it's very unclear how it's working. How is it actually creating the same kinds of abstractions that humans might create that might be generalizable to other domains? So now there's a new ARC prize, $700,000 grand prize, and the ARC, it's using the so-called ARC2 data set, which is much harder than the ARC1 data set. And now this O3 model gets less than 5% accuracy. Okay, so my group wanted to do something a little different. So Cholet's group said, okay, we have to make these problems harder. We have to defeat these AI systems. My group was saying, we really want to understand how these AI systems are doing these kinds of problems. So let's make the problems easier and really try and understand on these much easier problems how these systems do. So the way we made the problems easier was we tried to isolate various concepts so we could understand how well these systems were understanding different kinds of concepts. And this was work with some postdocs and students at Santa Fe Institute. We called this the ConceptARC data set. And what we did was we created variations on ARC tasks for each of, we came up with 16 very basic concepts that were spatial or semantic concepts like the idea of the center of something, the idea of inside versus outside, the idea of counting. And here's an example. So here's a task with 3 demonstrations and a test input. And I think if you look at this, you can see very quickly that the rule is remove the bottom object. Okay, so that was meant to be easy for people. And in fact, we tested humans and some other programs that had been tested. This was before this latest, the O3 challenge. We tested GPT-4 and they all got this correct. But we also wanted to do, as Anna Ivanova said in her paper, don't just look at one example. Here's another example of top and of understanding the concept of top or bottom. Color the top row of an object red. And everybody got that one right. But here's another example. Remove the top and bottom object. Well, here, humans had no problem because they have a very good abstract understanding of sort of top and bottom. But the GPT program got this incorrect. And there's some other examples, I won't give them here, but we found over all of the different concepts that we looked at, where we created many variations on a given concept, that humans were very, very good at all of these. Whereas the GPT-4 and the GPT-4 vision systems were very poor. But now we have reasoning models, and we're trying to understand the reasoning. We found that O1 Pro actually gets this one right. And I won't go through the details, but it explains its rule, and it actually gets the kind of explanation that a human would get. But on a different set of problems, here the problem is to extract the objects from the noise. It completely fails, and we see that it's not getting the kinds of abstractions that humans get. It outputs a ton of quote-unquote chain of thought, but it's really not going anywhere and gets the wrong answer. So just to summarize, overall, evaluating cognitive capacities of AI systems is very tricky. We don't know what the right benchmarks are. We have problems like data contamination, shortcuts, lack of robustness, lack of transparency on what the systems are actually doing. And the big question I think everybody in the AI community is having right now is what kinds of benchmarks or experimental methodology will provide insight? Can we provide methods from, say, developmental or comparative psychology, which, as Mike Frank says, also evaluate alien intelligences? Or, to lead into Allison's likely comments, is doing this kind of cognitive evaluation on AI systems entirely the wrong approach? I'll stop there. Thank you.
I want to express my thanks again to Janan and Sean for what I have to say has actually been a surprisingly wonderful set of talks. It's really hard to do interdisciplinary work, as I know, and to try and get everybody to be interested in something that crosses disciplines is really hard. And it's just been incredibly fun to be in the audience and think about all of these different kinds of questions. So I think it's been a great demonstration case for natural philosophy. And I think that probably has a lot to do with Sean and Janan in particular. So what I want to suggest is that the entire way of thinking about what AI systems, and more particularly what large model systems can do, as if they were agents, as if they were intelligent agents who we were giving IQ tests or cognitive tests, the way we do with children or animals, that entire way of thinking about them is misguided and wrong. And I've made this argument in two papers, one with Henry Farrell and Cosma Shalizi right here at Johns Hopkins that just came out in Science, and then a longer one with some more examples. And essentially, the argument is there's a kind of category mistake in thinking about large models as if they were like individual intelligent agents. Instead, I think we should think of them as being like what we've called cultural and social technologies. So essentially, the idea is that as long as we've been human, one of the things that we've done is find ways of getting information from other humans. So language is obviously the sort of example of this, but we have many other examples where the reason why we do so well, this is a point that Rob Boyd and Joe Henrich have made, is not necessarily because any individual agent is particularly smart or capable, but because we can get information from other agents. And Boyd and Richardson talked about this as being the cultural niche. And as I said, you could think of us as starting out with language as the sort of example of this kind of cultural technology. But in the course of human history, what we've done is develop increasingly powerful ways of getting more and more information from more and more people across greater gulfs of space and time. So if you think about starting out from language, we have pictures, we have writing, we have print. Once we have print, we have ways of accessing that information, not just distributing it, things like libraries or internet search or Wikipedia. And the sort of another feature of what we've done over time is not only have we had these new technologies that allow us to access information from other people, but we've also had new technologies that allow us to coordinate our information, coordinate information and action with other people. This is a point that Henry Farrell has made. The things like markets and bureaucracies and states, those are all mechanisms that allow many, many people to agglomerate their preferences and actions. And all of this, of course, predates even having a computer at all. Um, and to say that large models are like this is not to trivialize them. On the contrary, these changes in cultural technologies and social technologies have been the things that have completely transformed the world for good or ill. If we want to simply bring another intelligent agent into the world, as Anil suggested, we have a very good method for doing it, and it's much more fun than trying to make an AI system. Um, but actually, bringing those extra agents into the world, sadly, doesn't really transform the world the way that something like print or writing or libraries or markets have transformed the world. So this is not a debunking story. In fact, in some ways, it's maybe a rebunking story. These are things that make an enormous difference. But they don't make an enormous difference because they're a golem that has come into the world and now is a super intelligent agent. They make an enormous difference because of the way they put together, agglomerate the information that humans already have. And I think it's a really important point that the only reason why the large models work is because they're combining all the information that's on the net. I'll get back to the grandmothers in a minute. And in fact, I think that the really big thing that happened, not in AI, but in around the year 2000, and Alvey talks about this in his book, is that around the year 2000, all of these different forms of cultural technology were turned into bits. So around 2000, you get the first digital movies, you get digital cameras, you get PDFs, you get JPEGs, you get HDTV. So suddenly all these different forms of cultural technology are all infinitely reproducible and instantaneously transmissible. And once that happened, it was just a matter of time before you got things like large models that could access and organize all this now digital information. Um, Now, you might think, well, but that's not what these things are like, right? Like I sit there and I say, talk to ChatGPT and it asks me questions and I answer and it says, oh, I'm sorry, I'm just a large language model. Um, uh, but actually, it's interesting that when you think about the way that these cultural technologies have typically worked, a very common means of transmitting information, because we humans, as Jennifer was saying, are so good at conversation with agents, is to treat the cultural information as if it's coming from a kind of fictive agent. And here I can get back to the grandmothers. This picture that I love of the grandmother and her grandchildren, what that grandmother is actually doing, sorry, is reading a 100-year-old version of Winnie the Pooh, a 100-year-old edition, first edition of Winnie the Pooh, to her grandchildren. So what she's doing is conveying 100 years of information in the form of a fictive agent, namely Winnie the Pooh, right? And in fact, if you look historically, you can see that if you look at in forager cultures, for instance, you get Polly Wiesner has described this. During the day, everyone's out doing things, but at night, people sit around the campfire and tell stories. They talk about myths. They talk about the big structure of the community that they want to pass on to the next generation. And having these fictive agents is a very effective way of passing on that kind of information. People understand things in terms of fictive agents. Greek gods are another kind of example. Um, I say here, don't tell everyone that I said ChatGPT was a god, or if it's a god, only like all the other gods because it doesn't exist. And interestingly, if you see the changes in in print technology, which I think is one of the most dramatic examples of the way that new technologies can transform the world. In the 18th century, there were changes in print technology, which meant that print was now something that everybody could do. Everybody could produce a pamphlet. And one of the interesting things that comes from that is the rise of the novel. One of the first things when you actually have print easily available is that you start to get stories about individual people as a way of conveying and transmitting information about new ideas about how the society or the world could work. Um, and if you sort of switch to the other idea about the technologies, the sort of parallelism of thinking about markets and states as agents, of course, it's notorious that we treat markets and states as if they were agents. So we'll say things like, the market is punishing Trump for his tariffs. This is actually the cover of Leviathan, Thomas Hobbes' book. And I think it's really interesting that the way that Hobbes wants to illustrate this idea of a state that's controlling the individuals is by having a big giant who's the Leviathan, who's the state. Not only is this natural, but in some ways it's the right way of thinking about things like these social technologies. I think there's a genuine sense in which something like a market or a state or a bureaucracy has a kind of information processing capacity and an action capacity of its own, that if you wanted to describe it, even though it completely supervenes, as we philosophers say, on all the individual humans who are making decisions in the market, there's a sense in which a market or a state does something that's beyond what just the individuals can do. And of course, that's why books and libraries and markets and states are so useful and transformative for humans, because it gives us this way of having a compressed, usable representation of all the knowledge that other humans have, a way of solving coordination problems between ourselves and other humans. So if you have this perspective on what large models are doing, and let me just say, it's not that AI could never produce intelligent agents. I think there are ideas in robotics and reinforcement learning that are going to produce something that actually looks like intelligent agents. The point is that large models are not such agents. What large models are summaries of lots of information about individual people and methods for accessing that information in an efficient way. But then that raises the question, that to go back to the core of Melanie's talk, which is, how could you evaluate these kind of fictive agents, and does it even make sense to evaluate them? And here I think it does make sense, but it makes sense with a very different lens than the typical sort of, let's have an IQ test for an LLM lens. Because in fact, these cultural technologies, as I say, completely transform the epistemic and cognitive capacities of humans. We can do things once we start writing that we couldn't do before we had writing. So I think one way of thinking about it is, what kinds of capacities do different kinds of cultural information or social institutions enable? So if you think about something like Friedrich Hayek's account of markets, what he says is, well, markets give you these particular kinds of information processing capacities that you wouldn't have had before. If you even think about libraries, right? Libraries have capacities, let you have capacities that you couldn't have before. Even though it doesn't seem to make sense to say, does the UC Berkeley Library know more than I do? Well, yeah, it's got more information in it. And as a result of that, I can know much more than I could without the UC Berkeley Library. But it's just sort of a category mistake to say, does it know things that I don't know? And just a little side point that I was thinking about, people, when people have described this idea, will often say, oh, well, libraries, yeah, like libraries, that's not a big deal. But in fact, Berkeley has a whole discipline, library, what used to be library science and is now information science, which is just about how hard it is to figure out exactly how libraries work, how it's possible to access information from libraries, what the best way of encoding the information is, what the most efficient way of accessing that information is. These are really live, interesting questions. And I think those are the kinds of questions that you should be asking about LLMs. Another way of thinking about it is that you could ask, how do these technological tools in general expand human abilities? And here I'll mention the philosopher Andy Clark, who for a long time has been talking about the way that human cognition depends on these various kinds of external tools, from language to actual tools to things like writing. So you could ask in general, how does having these technological tools expand human abilities, and how do these technological tools, large models in particular, expand human abilities? And lastly, I think there's a very interesting question, which is kind of what I wish my colleagues in the social sciences were doing more of, which is what kinds of capacities come from these collective intelligences, these things like markets and states? What happens when you have a whole group of people together working in an institution? What kinds of capacities does that enable? And how do different kinds of institutional structures enable different kinds of capacities? So I think Melanie had some beautiful examples of empirical questions that we could ask, the right empirical questions about what it is that these systems are doing. And I think those results are going to be very relevant to these questions. But I think the philosophical framing of these questions might be much more productive if we thought in terms of cultural technologies rather than individual agents. So let me stop there.